Hello, everyone. Good morning, good afternoon, good evening, depending on which part of the world you're watching us from. I'm Mudit. I'm one of the founding members of AI Planet, and I'm super happy to see you here. Let me quickly go across platforms and check if you're live seamlessly. So, if you can watch me, just put on a comment so that I can see that yes, I'm live and you can connect with me. You can hear me perfectly. Meanwhile, I'm also going and doing a quick check. As you know, as you can see in the in the description of this particular session, this event, we are going to talk about creating pseudo data with GANs with Hasan Ali. So Hasan is already with us in the backstage, but let me quickly go and check if you're live because that's very important. I don't want anyone to miss out. Yes, I see Tarini's comment. Thanks, Tarini. Let me go and check on other platforms also. Yes, I see a comment from Innocent. Hi, good to see you. Hi, Pradeep. Hi, everyone. So, at times, what happens is there is some slight lag for comments to show up here. So, but yeah, I think we are live across platforms. So, let's get started. First of all, thank you everyone for joining in. This is one of those sessions which we published with a slight of delay, and I'm really glad and thankful to everyone who is joining now at this point in time because this particular session is quite exciting for anyone who is into data science. Why? Because we're talking about GANs and then building pseudo data, which can be very useful in several applications. To talk about AI Planet briefly, we are a global community of data science. Many of you might be aware of us already, would have been interacting with other members on the platform. We are a global community of data science enthusiasts from 150 plus countries. As an enthusiast, you can learn on our platform for free of cost, and our vision is to educate and build AI for all. These sessions that we organize is an endeavor to connect you with AI leaders live. And this is where every Saturday we bring a change maker who comes and educate for the community for free of cost, and you can go and learn from them live, interact with them. So today we have Hasan Ali with us. Hasan is one of, interestingly, he was one of the initial contributors who came forward when we were starting AI Planet. He's a data scientist and a founder of Pulp Vision AI. He's an entrepreneur at heart and has been working extensively in the industry of energy sector. He's currently based out of Sao Paulo in my same time zone, which is perfect. And yeah, he's here with us on the backstage. So let me quickly bring him on the stage. So yeah, hi Hassan, good to see you here. Thank you so much for being here.
Hi, Mayat. Thanks for having me here and having such a warm welcome. And I welcome everybody who is here with us live and who will watch us later maybe.
Yeah, thank you. So, without any further ado, I'll probably give the stage to you. You may feel free to obviously introduce yourself again or the topic because you're the best person to do it. So, over to you, Hassan. I'll go to the backstage. Important note for those who are joining, those who have been joining every session, they know you can put in the your questions in the comments, and we will be having a close look at them. But if you have any questions, so do not feel free to hesitate because we will be picking them towards the end. So you have to put them as and when you come across them. Okay. And yeah, over to you, Hassan.
Thank you, Vidit. All right, so I can see some of the chats already. First of all, I would like to thank AI Planet and everybody who has joined with such a short notice. So, yeah, without further ado, let's jump right into the topic, which is generative adversarial networks. Now, before we so Google Krishna is saying DeFi is nice, maybe some feedback from with it. But anyways, so before we dive into what GANs is and how to build GANs for pseudo data, or maybe numerous different applications, how many of us here do have some experience with deep learning or machine learning? Just want to know a little bit more about you before we move ahead. How many of us are students here, or maybe people who are practicing data scientists, data analysts who want to take that dive into deeper AI space? Nice. I see. Great. Cool. So I'll try to make this as simple as possible. I will try not to use any of the jargons or any of the complicated words and make it as simple as possible. So yeah, let's straight away move on and understand GANs, Generative Adversarial Networks. So, the objective of today's session will be to introduce you to GANs, some of the challenges that we face with GANs, and numerous applications that are there. So, we will also discuss about motivation behind generative models, then the GANs architecture and objective, and some of the applications that we can build with GANs, for example, DC GANs. So, generative adversarial networks, which is GANs. Generative means a generative model which generates data. It could be images, it could be videos, it could be signals, it could be text, it could be anything that you want. So, generative for generating data. Then, adversarial. Trained in an adversarial setting means adversarial basically means that wherein you are building or generating data by attacking it at the same time. For example, if you are training an image classification model, and then and that the objective of that classification model is to classify between dogs and cats, okay, and suddenly you produce an image which is very confusing, right? Whether it's a cat or a dog, or maybe you have somehow synthetically or with Photoshop you have changed that image. So that image would be more like an attack to the model, which would rather make it confuse. And if we are using such images in the training data, that would help our model to become more robust and strong towards such adversarial attacks. So adversarial basically means that testing our model with different situations and different input data so that it becomes stronger and more robust. Now, having said that, the best way how you can benefit from this workshop is to have a pen and paper, write all the questions and all the things that you think are important. And when we are concluding the session, then ask me all the questions that you can. And that would be, I think, a very fruitful way and a very satisfying way to learn maximum or take the maximum benefit from this workshop. All right. I'll be saying a lot of things, maybe, and some of them might confuse you, or some of them you might feel that you have some questions. So I think it would be great if you could just write that down and we can discuss them later. Okay. All right, moving on. Then networks basically like any deep neural network. So generative to generate data, adversarial to attack that generative model so that it becomes more robust and more intelligent and more stronger, and a network of such combination of generative and adversarial. So that's the overall high level overview of GANs. Now, why generative models? So essentially there are two types of model generally. One is discriminative models, which basically given an image X, they predict the label Y. So essentially what they do is they estimate the probability of Y given X. Discriminative models have several key limitations, which is they can't model the probability of the input on their own, right? I mean, there is no pre-assumptions about the input data. It could be anything. That is the probability of seeing a certain image. They can't model that. Thus, they can't sample from probability of X. That is, they can't generate new images. Whereas generative models in general cope with all of the above. They can model probability of X and they can generate new images. Now, this is the magic of GANs. We can create an image which is this from the ground truth, which is this. So this is the synthetic image, which is the adversarial that it has created from the ground truth, right? So we can clearly see that this is not as smooth as the ground truth data, but it still looks and feel a lot similar. So to humans who are like the most advanced AIs at the present scenario, it might look totally different, but maybe to machines or maybe to naive AI systems, those still can be fooled with such images. Now, here's a question for everyone. Among these two, which one do you think is generated by a GAN model? And I think if you look closely into this, you will be able to find out. So let's say this is image one, and let's say this is image two. Which one do you think was created by a GAN model. Number two, all right. Okay, so maybe I can come back to this later. While I assume everybody, I'll leave everybody in suspicion. Cannot find image two. Maybe difficult to tell since my internet is a bit weak. Okay, all right. There is difference definitely. Now, if you kind of focus on her necklace, so there is a difference that you might find. One of them is more defined, while the other one is just kind of imitating the pattern. But anyways, moving on. Now, this is something else also. So this is a tool by NVIDIA wherein you input this and it will create a green grassland for you. You with a pen input this and it will create a mountain for you. And this is very useful for image editors, for photographers. And this is a very popular NVIDIA tool wherein you just input a certain brush stroke and it will automatically create the rest of the painting for you, which is another application of GAN. Now, let's try to dig a little bit deeper into GANs. Right? We have understood on a very high level overview what GANs look and feel like, what their objective and tasks are. Now, let's dig a little bit deeper into their working, their architecture, and a little bit of maths behind the overall topic. Now, you would be amused to know that the person, I would not name the person, but the person who basically invented the first GAN thought of this idea when he was at a bar and he was chilling on a Friday evening drinking his beer. And that's where he got the idea of GANs. He went home, he coded the entire thing and did it for the next few days. And he got the first GAN model working. He wrote the research paper. And I think within a couple of weeks, within a few weeks, the first GAN research paper was out and it changed the entire research picture. I think till date, one of the most popular research paper is on GANs. So you see how Friday evenings can be fruitful and revolutionary for the entire data science and AI community. But anyways, GANs. So there are essentially two parts of it, which is the generated part, which generates the data, and then there is a discriminated part, which discriminates the data. Now, if you look at this architecture, we have a bunch of real world images and we feed in a sample to this discriminator. Okay. Now, this is a latent random variable, which means this is just a function which generates noise. Okay. This is a generator which generates noise with the help of G. We have this input. This is a generator which generates noise with a latent random variable and creates a sample from that noise. The role of the discriminator is to discriminate and distinguish the difference between the real world sample and the sample which is generated by a generator. Now, this difference, which you can call as D, is basically evaluated by a discriminator, that how different these two images are. And on the basis of it, it creates a loss. So the generator generates in the image and the discriminator tries to differentiate that image from the actual real world sample, and based on that difference it creates a loss. Now, the role of the discriminator is to distinguish and discriminate and maximize that loss, right? While if you think about the generator, his role is exactly the opposite. His role is to minimize that loss and create images which are as close to the real world images. So if you think about it, you will visualize this in your mind like two parties which are kind of constantly trying to win upon each other. The discriminator is trying to distinguish the images while the generator is trying to generate images, so that the discriminator is not able to distinguish, or the generator tries to fool the discriminator. So you can think of it like as a min max solution, where the discriminator is trying to maximize the loss, where the generator is trying to minimize the loss at the same time, and both of these things are happening simultaneously, right? So Z is some random noise which is input to the generator, and Z can be thought of as a latent representation of the image. Now, so what happens is that we lock the generator, right? So we feed in the sample to the discriminator so that the discriminator trains itself. Okay, so the first step is that we generate the samples, the real world samples, and we train the discriminator so that the discriminator is aware that okay, these are the real world samples. Okay, and we back propagate the error to update the discriminator weights to basically train the discriminator. That's the first step. The next step is to train the generator. Now the discriminator is trained and he knows, or she knows, how the real world images are. Now it's time to generate that, to train the generator, and it will create image samples, or could be noise, could be text samples, could be video samples, could be just sensor data. It can generate basically anything. So let's say it is generating image samples and now giving it to discriminator, and the discriminator is trying to identify which one is real and which one is coming, I mean, which one is coming is actual data and which one is just some random noise. And it gives the loss, and that loss is used to update the generator so that the next time it can create a better image or a better sample. So this loops happen wherein the generator keeps on generating samples, and the discriminator kinds of eliminates those samples by providing loss, and then that loss is used to again update the generator until a point is reached wherein the generator is able to fool the discriminator, and it produces images or samples which are as good as real. And once that point is reached, we say that our model is now trained. And then what we do is that we detach this generator and use it for generating similar kind of samples. And as I've already mentioned, keep writing notes and your questions, which we'll address at the end. So this is a generator in action, which it is trying different data distributions and then improving and evaluating itself. Now, this is GANs mathematical formula. We really don't need to go into the details of it, but just to give you a very intuitive feeling about it, we are working on a minimum max function where we want to minimize the maximum loss of the discriminator, right? So it is formulated as a min max game where the discriminator is trying to maximize its reward, which is to maximize the loss between the generated images and the actual images, whereas the generator is trying to minimize the discriminator's reward or maximizing its own loss. So that's why it's more like a min max situation. Generator tries to minimize the discriminator's reward or maximize its own loss, and then the discriminator is just focusing on maximizing its reward. And this is something which is known as the Nash equilibrium of this particular game. So this is something which is known as Nash equilibrium, wherein both of them are constantly fighting towards each other to win over each other. Now, this is the mathematical algorithm how we train the models, and this is the generated results. If we have an image data set which has faces, these are some of the faces that will be produced. And this was also the part of the research paper which the person, which I'm not taking the name of, released. This is a very famous CFAR dataset, and these are some of the images which were produced artificially by using the CFAR dataset. Now, this is a very popular use case by Airbnb actually, and some other companies combined. So Airbnb wanted to have some data about the bedrooms. So they wanted to have more data of bedrooms, bathrooms, their different sections of the house, so that they can train their models on. And they could not use their own data because they have some privacy. The customers, the users who own these houses have some privacy concerns, right? So they generated this data on their own using DC GAN. Just another use case. Now, this is the general architecture of a deep convolution GAN. We have the latent variable, then we reshape it, the convolution layer 1, then convolution layers 2, convolution layers 3, 4, and then the final layer. So we replace the fully connected hidden layers, which are the dense layer, with convolutions. Fractional strided convolutions is used in the generator. And inside the generator, we use ReLU for hidden layers and TANH for the output layer. Nice. So another thing that we can accomplish with GANs is that we have, let's say, a data set of man with glasses and man without glasses. What we can combine it to produce is a woman without glasses. Or if we combine another set, we can just then create another set which is women with glasses. So this is like if a generator knows the distribution or the latent distribution of this data set, then another generator knows the latent distribution of this data set, and then for this data set as well. So we can kind of combine these models to create another one which creates such images wherein it can put glasses on your face if you are not already wearing those. And any examples that you see in your neighborhood or surroundings for this? What do you think all the Snapchat filters are based on? Wherein you can look old, you can look younger, you can look funny, your face can look distorted, you can have a mustache, a beard. Where do you think that is all coming from? Now I think you might have some idea where. Now let's come to the part 2, which is advantages, the challenges, and some solutions for GANs. Now, GANs is not something that always have success. That you decided, let's train a GAN model, let's put in some data, and let's generate some images. That's not how simple it is, although it might sound. As you can see, it tries to solve a Nash equilibrium, which is a min-max problem. Not always will you find a scenario where it is able to solve that. So, some of the advantages of GANs is that there are plenty of existing work on deep generative models, Poser and machine, deep belief networks, variational autoencoders, which is like a more substitute or more like a younger brother of GANs. But and why GANs? So sampling or generation is straightforward. Training doesn't involve maximum likelihood estimation. It is robust to overfitting since generator never sees the training data. And empirically, GANs are good at capturing the modes of the distribution, how the data is distributed in the data set. Now, talking about some of the problems with GANs, the probability distribution is implicit, not straightforward to compute the probability of X. Thus, vanilla GANs are only good for sampling or generation. So, vanilla GANs means just plain and normal simple GANs. Now, there are a lot of different kinds of GANs. There is cyclic GANs, there is cartoon GANs, which creates the cartoons. There is a DC GAN, as you saw. So these are like more extended versions of GANs, which solves different problems of GAN, or they are very specific to specific use cases. Vanilla GANs are just the more fundamental GANs which were initially built, and then we have a lot of research around GANs, which led to more GANs, more research paper on GANs like cyclic GANs, like TC GANs, comic GAN, and there are like endless lists. I think there are somewhere around more than 50 to 100 research papers on just different types of GANs that there are. But the vanilla ones are only good for sampling and generation. Now the training is hard, no doubt. Sometimes it does not converges, which means sometimes it's not able to achieve or win over the discriminator. The generator is not always able to win over the discriminator, right? So that's basically achieving a basically never converging. And then model collapse. We'll talk more about this. So let's first talk about non-convergence. So deep learning models involve a single player, which is this player tries to maximize its reward or minimize its loss using any optimization algorithm like gradient descent with backpropagation to find the optimal parameters. And SGD has convergence guarantees under certain conditions. But the problem with non-convexity, we might converge to a local optima, not a global one, but a local optima. That is one of the problems. Now, GANs instead involve two more players, a discriminator, which tries to maximize its reward, and a generator, which tries to minimize the discriminator's reward, which is minimum of maximum of d comma g. D and g are the discriminator and generator, and v is the loss function. Now, SGD was not designed to find the Nash equilibrium of a game. The stochastic gradient descent is not designed to find the Nash equilibrium. It is just designed to find the optimal parameters which can give you the minimum loss for one particular player. Here we have two players, and sometimes they can be more than two as well. So that is one problem. We might not converge to the Nash equilibrium at all. Now let's understand the non-convergence. Okay, so think of it like in this circle, if you have a point on the circumference, okay, this is the point on the circumference. As it's moving in this direction, the x is increasing, right? The x value is increasing, but at the same time, the y value is decreasing. Yeah. Now it passes this and comes here. Now, if you notice, the x is decreasing, but the negative of y is increasing. So basically, what we are doing here is if we try to minimize one, the other increases. If we try to minimize the other, if we tries to minimize y, x increases and vice versa. And we are not able to basically arrive at an optimal point wherein both of them kind of balance each other, which is basically the point of this min max equation. Now, the second problem is model collapse. Okay, I see there are no questions till now in the chats, which could mean two things. One is either we are just too much involved in the topic, or it's just going over to the roof. Anyways, moving on. So, what is model collapse? So, model collapse is a situation wherein, so let's say we want an output like this. This is the target, okay? And we train a model, and it is, let's say, able to win over the discriminator as well. But it produces images which are just weird. For example, let's say this was expected out of the model that when the model is trained, it should create images like this, right? And the process how we would arrive at that is we started with one dot, then we increased it to a bunch of dots. The model is improving itself, the generator is improving itself, and it's trying to imitate the actual real world training data. This is at epoch 0, this is at step 5k. It has a bunch of points, more points, then a circle of points, and then now it's kind of reducing those points until and unless it reaches this status. This is the expected outcome, that this would be the process at 5k steps, 10k steps, 15k steps. This should be expected outcome from the model. But what we are getting from the model is something like this at step 0, at step 5k, 10k, so on and so forth. So basically it's not able to imitate the data, right? Now here are some real world examples. All of them are just generated from the different GANs. Here are some solutions to the earlier proposed problems. One is mini batch and other is supervision with labels. Now, mini batch basically means that at model collab, the generator produces good samples, but a very few of them. Thus, discriminator can't tag them as fake. To address this problem, let the discriminator know about this edge case, wherein if the discriminator knows that there will be some samples which would be very good, so basically let the discriminator look at the entire batch instead of single examples, which means instead of giving one sample to the discriminator, we give a bunch of samples to validate, to test, to basically distinguish for. If there is a lack of diversity, it will mark the examples as fake. By lack of diversity means there is a huge variance between the samples in the batch. Thus, generator will be forced to produce diverse samples. So, model collapse is basically when the generator is not able to produce expected output, but still, how come the model is trained and how come the model is able to win over the discriminator? So that happens when, although the generator is not working well overall, but it is still able to produce one or two cases wherein in those cases the discriminator can't tag them as fake, right? So address this problem, we don't give just one image or one sample to the discriminator to test, we give them a batch of samples, which is basically what? Mini batch, as we usually do in when we train deep neural networks. Now, another thing that we can do is we can provide some supervision with labels. Label information of the real data might help. Instead of just giving real or fake, we can give more labels like car, dog, and so on and so forth, and fake to the discriminator basically. Now, these are some of the applications of GANs which I was talking about. For example, there are different modifications in GANs. There is energy-based GANs which can create artificial energy. I've been working in the energy-based sector, and we use a lot of energy-based GANs to create different data sets, pseudo data sets for the energy sector, which are used for training our models sometimes. Then this is just the Airbnb example with more bedroom. This is for creating artificial celebs. This is if so. This is a model which can create the 3D poster of your face if you just input the front of your face. It can basically articulate and interpolate how do would you look in different lighting condition, with different poses, different elevation, and so on and so forth. Then same goes for different, for the retail industry as well. We can create images for different beds, furniture, lamps, fans. The same happens to be for fashion industry as well. We can create artificial data sets for different clothes, jeans, boots, so on and so forth. Infogan is also another kind of GAN which is able to create text which looks as if it is something generated by it just creates information which looks real. If you want to create text or some information which is very close to the real world grammar, real world sentences, infogan is your way to go. Now, conditional GANs, some of the applications of GANs, and then we will summarize this session, and then we will move on to our questions for today's session. Great. Awesome. So conditional GANs, MNSIT, they just generated conditionals on their class label. We are generating these samples. Then applications, bunch of numerous applications. You give a black and white image, you get a color image. You give a sketch, you get this as output. You give a photo during the day, you get a photo. How would that place look in the night? And most importantly, this one, wherein it can convert from a satellite view to a map view, which is just immense. And you would be surprised to know a lot of these models are used by Google in their different internal and external applications. Then this particular model is used by Tesla in their auto driving model to convert the real world scenario into just a segmentation map. So we have DC GANs for image to image translation, wherein this kind of GANs can convert an aerial view from a satellite to a map view, which you see on Google Maps. Then we have text to image synthesis. How many of us have heard of DAL E, which is kind of creating waves with its text to image model? You give in the text, let's say you write Shah Rukh Khan sliding on the moon, or Elon Musk um, riding a bike, and it will show you those images, which are not real, but it will generate those images for you. So that is the technique and technology and the research dull E is based on is different, while we can use GANs also for text to image synthesis. Like this small bird has a pink breast and crown and black primaries and secondaries, and it creates that bird for you. This is the model for that. Then face aging. If you remember, there was some time back there was a Facebook model, which I think there was an app which used to show you how you look when you would be old. Behind that, a GAN was there at those times, because now there are different kinds of research for creating fake data, not just GANs. But at that point of time, there was the predominant research was just GANs. So that model was actually based on GANs. Face aging, conditional, and the advanced extraction would be coupled GANs, wherein you can produce images of the same human being but with different changes, like sunglasses, change in hair color, change in the beards, and so on and so forth, wherein a couple of GANs are working together to change different features. Summarizing the entire session, GANs are generative models that are implemented using two stochastic neural network, generator and discriminator. Generator tries to generate samples from random noise as input, and the discriminator tries to distinguish the samples from generator and samples from the real data distribution. Both networks are trained adversarially in tandem to fool the other component. In this process, both models become better at their respective tasks. And these are all the research papers that have a lot of content about everything that I have discussed today. And I think it's time for now us to jump into the questions that we have. Thank you so much for listening me, and I'm going to be here to talk to you more if you have any questions. Over to you, Madhut, if you can hear me.
Yeah, sorry, my Mac was on. I was trying to uh, unmute and come back to the screen. Thanks a lot, Hassan, for this quite, I would say, interactive session, and really like the way you explained it from the scratch. I have one question that I want to pick first, which is a quite interesting one from your sector, which is, can you share a few use cases of GANs in oil and energy sector? A bit unable to relate there.
Oh,
Yeah.
sure, sure. I think I can talk about them, but not really show them. So I can talk
Hmm.
about them. So when I talk about the energy sector, I talk about oil and gas. I talk about the electricity that we consume. I talk about the wind energy. I talk about the solar energy, right? It's basically everything. Now, we wanted to build a model, and this is pretty recently actually, wherein we wanted to build a model which could understand your domestic energy consumption, which is the energy consumption in households.
Hmm.
And we wanted data for that to build a model which is able to understand everybody's house energy demands. We would need, if let's say we want to implement in a country like Brazil, we would at least need 100,000 houses to train our model on. And
Hmm.
we both we all know that's not really practical and possible, right? So we created some data by installing sensors in different houses so that we could gather data from these houses. Once we had that data, we used that data to extrapolate and generate similar scenarios. So basically, from those five houses, we created some more data to understand and combine all the different scenarios that maybe 20 homes might have using GANs, which
Hmm.
were similar to the consumption of that house, but different at the same time.
Hmm. Okay. Okay. And are GANs, the models built on top of GANs, are they inherently explainable, or you have to use something like SHAP on top of it? Just a general question
So
because.
that's a totally different world, actually.
Hmm.
As we would go more into more complex deep neural networks, like for example, GAN is you can say maybe stage two of complex deep neural networks, where we are kind of combining two networks together. The explainability just goes out of the window. And at the same time, SHAP is something which just tells you the feature importances in a way. It is not exactly something which explains you 100%. For example, in cases of machine learning, you will be able to totally understand why a particular prediction came.
Hmm. Hmm.
Compared to in deep learning, you will just be able to understand and just explorate the reasons. Okay, this might be because of this, but you would never be 100% sure.
Okay. So on these lines, I have one question from Nilotpal. My question could be naive, but I'll put it across. I'm wondering if this would add bias to the data, given that the data you initially picked and then you augmented it.
Yeah,
Even.
definitely. That's a very good question, actually. It definitely adds data, but you have to be very specific about the data that you're feeding into the model.
Hmm.
So the
Hmm.
data preparation part is very important. Otherwise, either your model will fail, or if it will produce wrong or just bad images or bad samples, which would of no use. And in some cases, it will also produce biased data. So one, for creating and generating a GAN model, you need huge data set, and
Yep.
then you also need to be very careful on how you curate that data set. There should be a good balance of the things that you want to achieve.
Hmm. Okay. There is one. There are two questions. One is slightly. Let's pick one which is related to the subject, which is around the image that you showed initially. Gokul Krishnan is asking, can we de-blur the blurred image using GAN?
Yeah, we can do that. We can do deblur, we can do super image resolution, which is called super resolution. We can convert black and white to color. We can also convert an image to a video. So
Hmm.
just immense applications there.
Yep. Um,
Exactly, Google Krishna.
Yeah, so yeah, this was the comment on which both of us laughed. But yeah, there is one last question that I probably want to pick here. Is can this is slightly unrelated, but yeah, can generators in GAN be reversible?
So what exactly do you mean by GAN being reversible? Does that mean that, what do you mean by GAN being reversible exactly?
So well, I think if Sam is there, maybe he or she can clarify on this. Yeah, maybe I'll pick the next question from on top of this. I want to understand this particular thing from you. Like when you described about GANs, you talked about the energy sector. You were talking about the fashion sector also. Okay, so typically, where do you see? I mean, GANs being applied most in the world as of today's date, because there is a lot of yeah, generative AI is being used proactively across sectors. But can you also share some examples of where generative AI is not an image but more of a text, and it's being used today proactively? Yeah.
So I think everybody must have heard of Chat GPT, which has everybody has just gone bonkers over the internet over that.
Hmm.
Now, Chat GPT is not essentially based on GANs, but we can maybe build a model using GANs which can create and generate text data. It can also generate signals. So we essentially in the energy sector don't generate images, we generate signals, which is like 1D data, whereas images are maybe 2D or 3D data.
Hmm.
While we
Okay.
generate just 1D data, which are just signals, sensor data.
Hmm.
So And I think images are also just a 2D snapshot of a signal, because if you think about it, images are just a 2D numpy array. So in a way that, with that, I also have a hands-on model that we can train and see how a GAN model works. But I would like to first wanted to stop here and discuss some of the questions that you might have, rather than just going to the end of the session and then asking and interacting, because I really love to talk to you and see where everybody is in terms of their understanding and questions. Cool. So what do you think? Let's train a GAN model then.
Yep.
Awesome. All right. So Mudit, can you share the link with them in the chats, the Google Collab link?
Yeah, I'm sharing it on the chat. Maybe we can start because at times it may take a couple of minutes to reflect. Yeah.
Nice. So I'm gonna share my screen. Okay. All right. Perfect. So we are today going to create pseudo data for boots, t-shirts, trousers, jackets, a lot of different products that we see in the fashion industry. And one more thing, if you go on any fashion website, you will see a lot of models wearing different products, right? Very soon in the future, you will see models which are actually generated by AI wearing those products like t-shirts, boots, jackets, mufflers. All the models that you would see down the road would actually be generated by AI, and they would not use any humans. So if you think about it, they'll be saving so much. They'll be first saving the cost for arranging things, bringing a model, bringing a photographer, making the model wear those products, and then shooting and then putting on the website. Whereas they could just click a button, a GAN model would run, and AI pseudo human would be generated wearing that particular product, right? Such a big save in terms of time, money, efforts, everything. Now, if everybody's here on this notebook, try to connect with your respective Google Collab and then start running these cells. You might hear some noise from my background. I am right now, uh, so we all know that FIFA is going around the corner, right? And yesterday, Brazil lost. So the entire kind of country is mourning that. And you might see or hear some noise from my background in terms of people just crying. Okay, so no, just kidding. Anyways, let's move forward. So I'm gonna just plain and simple run throughout the code. I don't want to dig into the details of explaining the model, but still I want to. I can answer if you have any questions. So for now, I would just request you to run the different cells that we have. So basically, what we are doing is we are loading fashion data. We are separating the data into train and test. Then we will train our discriminator separately, generator separately, and then at the end, we will see how after every few epochs our model is improving. Okay. So, anyways, one second. This is training. Yeah. Okay, it has been trained. One minute. Losses. Give me a moment. So our model has been trained. We just need to find a way to visualize it. Just give me a minute here. So we have given it to. Okay, so this is like the first epoch. This is the result. Then next epoch, just random noise you'll see here. Now it'll start getting into shape after a few epochs. In the beginning, it's just random noise, which it is estimating from a Gaussian or the normal distribution. Yeah. Now, if you see, there is some vague patterns you have already started to see. This looks like a T-shirt here. This looks like a boot. This also looks like a boot. Right. So there are some figures, outline sketches have started to make sense at epoch 9 and 10, and it will only improve. Yeah. So while this is training and improving itself, you can go forward and ask questions in this notebook. Hmm. Far better at the 20th epoch. So yeah, while this will go till 50 epochs and we'll see more refined results, let's see if we have any questions here. Okay, I'll not scroll anymore. I'll just keep it here. Okay. Let me know if you want me to scroll to a particular section or area. It's epoch 40. And do you see how clear the images have become with just the 40th epoch? And I think you'll be able to see in your own respective notebooks. Nice, sweet. Sure, sure. So let's, while we have some time, let's go slowly and understand, if we can, a little bit about the architecture, the different losses. Okay, so here we are just defining the train buffer, the batch size, the test buffer, the number of dimensions, which is 28 by 28, which is the size of the image we will input into the model, number of train batches, which is total number of images divided by the batch size, would give us the number of batches, number of test batches similarly. Now we are loading the dataset from the fashion MNSIT data, train dataset, test dataset, now loaded, visualizing at this phase what are the different products here and how do they look like. Now we are defining our model, which is a GAN model, initializing a GAN model here. Self.gen would be our generator and self.disk would be our discriminator. Now both of these model would be sequential models. Okay, sequential basically means one layer after the other. So we have two separate models here, till right here till now, and both of them are sequential, which is one layer after the other. Defining a function which does self.gen bracket z, discriminate self.disk x, which is the input that you give here will go inside self.disk, which is the sequential layer. Okay, so now how to compute the loss. So we pass through the network and compute the loss. Tf.random the normal x shape 0 1 comma 1 comma self dot n underscore z. Now we are taking a random data, which is just a normal distribution of noise with the same shape, generating noise from a uniform distribution. Okay, and then we will pass that image into self dot generate, the generator. Okay, it will discriminate the x and the xgen, self dot discriminate x and self dot discriminate xgen, logits x and logits x. Now we will calculate the GAN loss with discriminate the real loss from logits x and discriminated fake loss from the logits xgen, which is basically the two losses from the real image and from the discriminator image. We will save them as discriminator real loss and discriminator fake loss. Now discriminated loss would be the discriminated fake loss plus real loss, and losses of fake data with label 1 is equal to generator loss is equal to generator loss logist x gen, and we will return both the discriminator loss and the generator loss. So we are calculating the generator loss as well as the discriminator loss here. Now computing the gradients, which basically means that we are updating the weights here, pass through the network and compute loss and then update the weights using that loss, apply those gradients, compute the gradients and apply those gradients, and then GAN loss would be if Israel, logits in Israel. So basically, if we are passing a loss which is of real data, then labels equal to tf.1s like logit, else labels equal to tf.zeros like logits, which means tf.zeros would like a zero numpy array, and then tf.compact be sigmoid cross entropy of the labels. So this creates the GAN loss, total GAN loss. We have individual losses and then we have total GAN losses. Now, this is the network that we are defining for generator. Okay. And this is the discriminator loss. Discriminator entire neural network. We have a dense layer, will reshape, then 2D layer, convolution. In the discriminator, we have an input layer, which is equal to dimension, and dimension is this, which is the image. So the discriminate, we have an input layer of this dimension, then a convolution, flatten, and at the end, we have dense one layer, which gives you one output. Okay. Now we'll create the model. We will create different optimizer for different models. This is the generator optimizer, and this is the discriminator optimizer. Now we will finally combine all the models. That this is the generator neural network, this is the discriminator neural network, this is the generator optimizer, this is the discriminator optimizer, and NZ, which is 64. If I 1 minute, NZ here, model can self.nz, which is basically just the shape. And now finally, when we have defined the model, here we are now writing a function to visualize, and then here just we are training and showing you the results after every match. So model.train input, and then we are testing and showing you the results here. Can we add inception v3 as discriminator? Video feed hiding. Can we also add inception v3 as a discriminator? um I believe yes. If you can change the discriminate, you can change the inception v3, uh, the number of the layers and the input shape according to this required. Like I think the inception v3 only accepts a particular amount of input shapes. It's not just accept everything. It only accepts particular shapes of input images, right? So if you can change your input here according to that, it will also be accepted by inception v3, and you also change the last layers accordingly and the losses there. So it's all about the optimization function, the losses, and the input and the output shape. Rest everything I think can still remain same, but inception v3 also has a lot of other layers than just convolution. So I think it would be a great experiment to see if we can, but I think I have a feeling we can do that with different a little changes here and there with respect to, yeah, as you mentioned, 224 by 224. So yes, I guess it can be you have to just change the loss function at the end, the optimization, and maybe we also might need to play around with the layers. And yeah, I think it would work. Awesome, nice, great question, great thought process. How what you have, Google Krishnan, amazing, sweet. So, having said that, we have reached the end of the presentation today. Some of us might feel it was a little overwhelming. Some of us might feel it's really informative. But at the end of this session, I think I would say gather something that are the future, and you should definitely after this session go over it again. And if you are into this field, GANs are something that you cannot miss. Although I've tried to cover most of the things here, but still there are a plethora of things that are yet still to learn. And having said that, I would like to thank everyone, gracias, who are into the session and took out their time. And we have Mudit here.
Yeah, I think we would maybe just second on that. We thank everyone who has joined, stayed till so far, and asked the questions. Um, we hope that this session was quite useful for you. And Hassan, a very special thanks to you for being so patient and creating this. First of all, this session on a short notice, and also going through notebooks and every smaller details. So thank you so much, Hassan. Really appreciate it. There is one last question if you want to pick it. Is
Yeah,
our
the RTX 306 is enough to try it on a local machine. So one thing that I should tell you is one RTX 3060 is not enough. But it totally depends upon how much data that you have and how much scope that you have to, how much scalable models you are building. Let's say if you are building for the masses, you might need more RTXs, right? A lot more than you think. But if let's say you are just playing with data and learning things and learning new things, RTX 360 would be more than enough for you.
okay? Thanks for answering that one last question. There are a lot of messages on thank you note. So thanks from our end also. And folks who are live right now, quick note: we have a series of sessions lined up. The next one is on uh, AI product lifecycle. We'll be covering about soon after that we'll be covering about AI in marketing. Then we have sessions on distributed ML and so on and so forth. So please stay tuned, and we look forward to seeing you again. And Hassan, thanks again. Uh, we are very much looking forward to having you again on the platform. Yeah. Thank you, everyone. Have a great week ahead. Happy weekend. Happy learning. Cheers. Bye.
See you guys. Bye bye.